Thanks a lot. Thanks to the organizers. I'm sorry that I was late this week. Like great talks. Okay, today I want to report. Okay, so it's the last talk of the day. Okay, and you see, imperfect fields is something kind of, it kind of got developed like recently in birational geometry. So my idea of this talk is to kind of at least show you that, someone has to do this, in a sense, okay? Okay? I will provide examples, okay? And I will report about these two projects, one with Stefan Schröer, and the other one with Fabio Bernasconi, Schneider, and Susanna Zimmermann, okay? And let me start with some motivation, of course. So, okay, why imperfect? Okay, so let me start with geometric setting, okay? K algebraically closed, and let's say in any characteristic. Okay, so you have seen, I guess, during this week and previously, okay, that if you start with X smooth projective over K, and you assume that the codirect dimension of X is minus infinity, then, okay, any dimension, okay, like any characteristic, any dimension, the MMP conjecture, let me put it this way, maybe conjectures with a plural, conjectures, okay, imply that you can modify birationally X and get a fibration. So X is birational to say pi from W B is a Mori fiber space. Okay, so in a sense, what is important, like for now, is that it's a Fano fibration, so some sort of minimal Fano fibration. Okay, and okay, this is proved like in some cases, okay, maybe with weaker assumption on X, okay, but at least like people think should be true in general, okay, and so the point is that this maybe a first comment, remark, okay, this reduction is useful in many cases, but like for instance, since we are doing it's a like Cremona group workshop school, is useful to study, for instance, algebraic subgroups of European K. Okay, I guess you have seen like that this. I don't want to go into this because this is like a topic by itself. So, but this is kind of interesting to remark. And so, why I talk about this, okay, is that if you assume that your characteristic, so characteristic of K is positive, and say that B is not just a point, okay, then you can look at the generic fiber of this guy, so K of B. This generic fiber is a Fano variety over an imperfect field. Okay, and let me just mint. Okay, this is a school. Okay, it admits non-separable algebraic field extension. Okay, so classical example, say F is little k p, okay, k algebraically closing characteristic p, okay, p, I fix p, okay, p is always the characteristic, and then of course you take this is unseparable polynomial. Okay, so this is the standard example to keep in mind all the time. Okay, what is tricky is the following, though. Even if you can say, okay, then what? So even if W is smooth. Okay, and this is, I mean, several talks already mentioned this. You know, when you work in the MMP, you start with something smooth. I mean, there's no way that you end up with something in general smooth. But say that the singularity is mild. But for what I can say, even if in W is smooth, okay, then the generic fiber may be not smooth. Okay, but only regular. Okay, you could say, okay, what the hell are you talking about? But like, so my point is that smoothness is something related to, so okay, let's say Keller differential. Keller differentials have let me write it this way, right dimension. Okay, the dimension of, like, locally at every point, the dimension of the variety. And regular here means that the Zariski tangent space has the right dimension. It means that Zariski and over imperfect fields, those two things, they do not coincide. Okay, smooth is stronger. Okay, you can guess why, right? Because when you differentiate, you get many zeros. Okay, that you wouldn't want to get. Okay, so when you generate your Keller, like, this is going to be much bigger than expected in general. Okay, good, very good. Nice. So let me write down an example. In my favorite characteristic, which is 2. Okay. So take this. So okay, let me write it like W over F. Maybe let me write it this way: little k Ts. This is defined by square plus T x1 square plus S x2 square. Okay, this is inside P2 over this field. This is a, okay, maybe so it's a kind of wild, this is the generic fiber, what usually in literature is called wild conic bundle, okay, even over P2, okay? This is the function field of P2, okay? Those examples exist, okay? So what happens is that this is, so let me write it, wild conic, which is regular, non-smooth, actually not even geometrically reduced. Okay, so this is something which geometrically becomes a double line. Okay, imagine that, so you see, the problem is that S, I mean, you cannot reabsorb S in the square, right? Add this, like the square of this, like, and then this becomes like, this can be reabsorbed by this one. So you get two lines intersecting like this. And now absorb this one as well. And now you get a double line, okay? Because we're in characteristic 2. Okay, so this becomes a square, right? So this is kind of the standard, like, would be the first example to consider here. Okay, good. Very good. So the slogan here. So let me put it this way: if you do algebraic geometry over algebraically closed field in characteristic P, at some point, whatever is your goal. But even think about Cremona. You want to study Cremona, right? So you reduce to Mori fiber spaces, okay? And then you have like this generic fiber, which is a fan over an imperfect field. And it's going to be regular, non-smooth. So my point B is that, so over imperfect fields, the assumption smooth is too restrictive. Sure. No, of course. I mean, say that now you take T, only T, and take, erase this, so take just S, okay? Then this is like something which geometrically is singular, as like a point, the singular point of the two lines. So it's singular at the point. And then you know, like kind of, when you, sorry, I'm saying something stupid. Like if you take this one, you take x naught plus S, because you can reabsorb this. What you can do, you can take kind of a double line denormalized along a point. This is possible. Or you can also take kind of two copies and then like identify a point of degree 2 and you get this. It can happen as well. I mean, no, you like that? I mean, you can do this. Like, so what is true is that this kind of examples to be regular, you need like at least 2 variables. Like, there you need. If you're just one variable, there's no way that you get a regular conic, which is so geometrically not reduced. So you need like. Okay. Good. Right. So all right. So the idea is that what we do is some kind of if you look at the classical literature over arbitrary fields, like say surface theory, okay, often the assumption you have is smoothness. Okay, so on Del Pezzo's, for instance, you look at the literature, classical literature, Iskowski, Manin, and so on. Like usually, either they work over perfect fields or they assume smoothness. There's always one of those two, right? And this is exactly the reason, okay? So let me start with a very classical theorem the first thing I want to discuss, which is Iskowski's theorem. Give you a so big doubt if I have to put a K here, like we discussed with Stefan, like it wasn't clear, like we found both of them anyway. Okay. So let me start with the classical theorem, which is by Castelnuovo. So this is 80, put a date, 1893, okay? Which is the famous rationality criterion. So you take S to be a smooth projective surface over K algebraically closed. Then S is rational if and only if so the regularity is the same as the H naught of omega S2. Okay, so those two numerical vanishing statements imply rationality. Okay, this is a very classical one. This is called irregularity, usually denoted by Q of S. And this is the bigenus. Okay, this is P2 of S. Okay. So this is very nice. And okay, the remark is that this is a birational statement. Okay, those two guys are birational invariants. Okay, so asking the vanishing. So basically, when you prove this, you can assume that your surface is minimal. So when proving the non-trivial implication, okay? Why do I say this? Because Minkowski theorem is a generalization of this, okay? So the idea of Minkowski theorem is like, take surfaces verifying this vanishing over an arbitrary field, and then what can you say about the surface, okay? Not gonna be rational in general, but at least what can you say about it? And that's the theorem. Okay, let me write it like this. So this is by Minkowski. This is put the year here. 1970. Okay. So it has to be a smooth projective surface. It's projective minimal surface. Sorry, I said that. Over F, any field. I'll try to be coherent. A big F for me is an arbitrary field. Little k is an algebraically closed one. Okay. So assume that S is geometrically irreducible. And this is a reasonable assumption when you work over non-closed field. And assume the vanishing. So P of S, P2 of S equal to 0. Then, so you have trichotomy, okay, trichotomy. So either S is isomorphic to P2, or S is isomorphic to a quadric inside P3, quadric, or 2, S comes with a conic bundle structure over a conic. Okay. Or 3, this is what I call the carpet. Carpet, when you hide everything, you know, like all the rest there. The Picard of S is generated by the canonical divisor. Okay. Right. So this is the statement. And let me just, right? Or, of course, or. They're not one excluding the other. I'm not saying this, okay? Of course, you can have, think of, I mean, the quadric, right? Over an algebraically closed field, this is P1 cross P1, so. Okay, so the first remark, let me just say this, but this is like pretty clear. This generalizes the Castelnuovo theorem, right? Because, okay, assume this for Castelnuovo, you have an algebraically closed field. Oh, this is P2, good. This is P1 cross P1, good. Those are Hirzebruch surfaces, okay? Minimal, I'm assuming minimal. And then the last step is to show that this never occurs over an algebraically closed field. Okay, that's how you prove it. This really generalizes it. And so, so remark, let me write it down. So first thing is that 1A. Minkowski implies Castelnuovo. And second remark, maybe let me say, one could think one needs very complicated field. I mean, if you take R, okay, this is already like an interesting statement. Already interesting. over R. Now you have, of course, you could have like, all these, the conic bundle will have like a different structure. Will be more, so here, for instance, already you have like two forms of the quadric, You have so over C, the pickup rank is 2, over R can be 1 or 2. So like here, you have conic bundles. You can have these real conic bundles swapping the special fibers. There is a lot of stuff to say. And here, I mean, this is like hard in general. Well, for R, now it's okay, but you can find like minimal real surfaces, del pezzo surfaces of degree 1 and 2. Okay, like there is stuff here. Okay, and now that's the moment when I take colors. So hopefully the yellow should be better than the others. That's what maybe not. I'm sorry. Okay, so I will modify this, adding us. Okay. Okay, so the first thing you should almost tell me what is the first thing I change in the statement. Okay. So regular. After this, I don't know how long the introduction. Okay, good. So this is the first thing. Okay, so here, what you assume on this, okay, what you want to assume is something general, more general. So you ask that there are no constant extension, okay, of this. Okay? So this can happen, right? Like that you can have like that. If you are, especially, like, you could have like this is like a purely inseparable extension of your field. Okay, this could happen. Okay, but this is is not very restrictive because you can always, you see, when you have your scheme over spec A, or over spec F in this case, what you can take the regular functions on it. Now you have a morphism. So you can always take this as an assumption. It is not restrictive at all. Okay. Okay, this is fine. This is fine. Let me just put this in parentheses because this is not wrong. Okay, but I would say that conic bundle, so genus 0 bundle, maybe conic becomes genus 0 such over a genus 0 curve. Curve. Okay, and this one says the same. Okay, so say, okay, this is a kind of statement which is like no surprise, basically. Okay, this is what happens when you do work over imperfect fields. Me personally, I hope to find like something completely different all the time. Like, okay, now we find something else. Like, sometimes it happens, sometimes it does not. Okay, but anyway, good. Okay, so let me make some comments on this. So see, I keep the color, okay? So S may be geometrically non-normal, even geometrically non-reduced. Yeah, this is really the problem, okay? In kind of just generalizing easily, because you could say about, like, okay, if it's, you take a surface, you base changes the algebraic closure, you have the statement, and like you see what happens, right? The problem is that it's singularity of S, so it doesn't behave well, okay? Like if you base change, you can get something which is non-reduced, so you cannot apply just the theorem straight, okay? Or it can be non-normal, like so a priori you could have other things happen. That's kind of the thing. And let me also make, sure. Absolutely. Thanks a lot. You're right. So very good point, Michel. Very good point. You say, okay, what is the omega here? Or if it's regular, it's Gorenstein. So for Gorenstein, you can define you can always define the dualizing shift, like the dualizing complex. And Gorenstein implies that this is actually a line bundle. Okay, so this is okay. You can do this. Okay, thanks. Very good point. And in the same spirit of Michel's comment, like say minimal. What does minimal mean? So minimal. It means so over algebraic closed field, you have -1 curves. Okay, but here you need a generalization of this. This means that S does not contain integral curves. So an integral curve C, such that C square C dot omega S is it's not -1, but it's minus H naught of OC. Okay? That's the thing you want to write. This actually implies that, okay, as for the case of -1 curves, that C is isomorphic to, if you verify this, is P1 over H naught of OC. So this is called in literature like second type curves, exceptional curve of second type, whatever, but this is what it means. Good. Cool. So just, I mean, this can be an extension. It can be a field extension. That's the thing. Or, if you want, can be also like, I mean, imagine like the Galois case, okay, like over the perfect, this is true also for the perfect case, okay? Take R over C. What you're allowed to construct is 2 minus 1 curves. So this can be also a product, like the product is also possible. This is in, I mean, right? This is 2 copies of P1 over C, right? Exchanged by the Galois action. Say it again, sorry? No. So OC. Thanks. OC of the curve. Yes. The other thing you can do is this could be a purely inseparable. Okay. Think about the conic because the characteristic 2. Hopefully you get this theorem. Like basically is dealing with characteristic 2. Okay. This extension of Vygotsky's theorem. This can be like a purely inseparable degree 2 extension in characteristic 2. So this is a kind of a geometric thickened curve, okay? Which is regular though, it's integral. Okay, good. So let me say something about the strategy of the proof. So good. I mean, okay. Let me do this case. So the classical case with a twist. Okay. So at least I try to pass like kind of the idea, the basic idea of the original proof and how we generalize this, because like to avoid sticking to the imperfect case. So let S be as in the statement. So S as in the statement in the statement. Okay. This is the lemma, the kind of key lemma. This is very classical, okay? Like it's not us by at all. So if omega S does not generate the Picard of S, there exists C integral curve on S with H1 of S equal to 0. Okay, this for me is not a genus 0 curve. Okay, for me a genus 0 curve is also one such that the H naught is 1. Okay, so you OC, thanks. Thanks a lot. Thank you. C square is, and for any C linearly equivalent to C, C prime is integral. Okay, this is a very kind of classical statements like you do in surface theory in a sense. Okay, so the idea is basically if this does not generate, okay, you come up with this movable curve, this movable linear system, okay, and what happens is that as you want this not to break, okay, into like irreducible components, okay. But this is not hard. I say that it breaks, then you take one component. And at some point, so for minimality, you can find this. Okay? So say like the proof is basically Riemann-Roch, so the proof is basically Riemann-Roch plus epsilon, maybe. Okay, and basically, this curve is the protagonist of the whole proof. Okay. All right. So let me write it here in yellow because it's related to imperfect fields, maybe. Okay. Is that in general, H naught of OC may be strictly bigger than 1. Okay? You could have like this curve has some constant field extension. This actually happened. Can be so if you want H naught of OC maybe purely purely inseparable extension of the base F. Good. And now let's do some geometry, okay? So now consider so the bundle associated to, let me write this way, let's see, okay? You check this is globally generated. So this induces F from S, a projective space, the N. Okay, let me get the numerology right. So H naught of L is 1 plus H naught of OC plus C square. This is a Riemann-Roch computation. Okay, so you see you have this, which is not 1. It can maybe no 1. You get that. This N is H naught of OC plus C square. And C square, of course, like verifies, so C square verifies the degree of F times the degree of the image, so V is the image. Okay. Right. And now you see this is the kind of the base like numerology you start with. Okay. And then you check which values you can get. And the proposition, which is, this is the almost classical case. The following, so assume that C square is not too big. Okay. Then you get what you expect. Either S is isomorphic to P2, or S is isomorphic to a quadric in P3, or to, so of course this is a C square equal 1, this is a C square equal 2 case, or S comes with a genus 0 fibrations over a genus 0 curve. Okay, and this is, of course, c squared equals 0 case, right? Okay. So, what do I mean with genus 0 fibration? Maybe I should say I just mean that the generic fiber has genus 0. Maybe I should also tell you like definition. Okay, maybe because I said genus 0 too many times, right? So C, an integral curve, is genus 0. So this is over F, okay? If H naught of OC is 1 and H1 of OC is 0. Okay, just because you have seen that there are like extensions over the function of the curve itself. Okay. Right, so maybe let me show you like a comment on the proof. So to show you like where one has to be careful. So comments on proof. Proposition. In the case the c squared is 2. Okay. Okay, that numerology tells me that a priori one could have h naught equal 2. So a priori one could have h naught of OC equal to. This is allowed. Okay? So you see, what it means is that you end up in, you want to end up in, of course, you want to show that it's the quadric, right? It's a regular quadric. Oh, I didn't say this. That quadric is regular. Okay? So of course, it's right. So it's a quadric, which is of course regular, because I assume it's regular. So, so here, if n is 4, you end up, you know, in a space which is too big. Okay, it's not a big deal. So take f. Let me write goes to p4. Okay, it's not a big deal. Like you can take carefully like a sublinear system. Of dimension 3. And so this is kind of, you get f twiddle from S to P3. And the image is a quadric. Okay? And now, what is the problem is that if you look at V, the image, this could be non-normal. Okay? But this is impossible. Could be a non-normal a priori. Okay, if you show that it's regular, we are done. Right. But the fact that h naught of OS is 1, plus the fact that, moreover, the fact that V is a quadric, tells you that give a contradiction. Why this? You see, because the quadric, even though in characteristic 2, you can really classify them. It's not hard. It's kind of maybe the only case where it's kind of really doable by hand. And when it's not normal, there are not many options. Okay? What you have, you see, 2 planes, right? Okay, basically, that's how you should think of it, like 2 planes, and maybe you can have Galois group move, you know, exchanging them. This is possible, or you could have a thickening. This is also possible. But like this is kind of gets in contradiction to this, because you know, if you factor over the normalization, you will get that this as h naught equal to 1. And this is never the case for the normalization of a quadric. Okay? And okay, so this means that this is normal. And then to show that it's regular, okay, so if it's normal but not regular, this is a cone. Again, it's a quadric, right? So the way you do this, you take some hyperplanes passing through the vertex, and then you take the pullback, and this gives a contradiction with the minimality of C, because basically it splits, and we assume that C doesn't split. Okay, so regular, then get contradiction from, let me write this way, minimality of C. Hopefully it's clear what I mean. Okay, like I'm taking the irreducible component which doesn't deform. Okay. Good. So this is like kind of the kind of idea. Let me. I don't want to get into the non-classical case, but I can tell you what happens. Okay. So a priori, for the non-classical case, so it means that C squared could be strictly bigger than 2. Okay? And so let me say that the key point is that to show that C squared is bigger than 0, then h naught of OC is 1. Okay, so this is the key technical point, okay? And to do this, you need to study, so it's kind of what we called inseparable pencils on your variety. So basically, you study pencils in the inseparable like kind of setting. I don't want to say more than this, but yeah. So we need to exclude this, and we need really like to study the geometry over imperfect fields. Okay. But still, what happens is that this doesn't occur. We come up with a contradiction. Okay. So. Okay, so in the last 15 minutes, I want to just say this. So say a glimpse under the carpet. Okay, so the carpet for me is that one, right? This is like a very kind of, so if one wants to study, especially if one is thinking about application to Cremona, one needs to study the birational geometry of Del Pezzo with index 1. Okay, this is like, you cannot bypass that. Let me, maybe, I want to make an example, which is showing a little bit, again, p equal 2, my favorite, about what can happen. Okay, so this is about what is called pathology and Del Pezzo surfaces. So pathology, I think, is a term, it's Mumford who introduced that, like in positive characteristics. So there is this very, very nice paper, I think it's like maybe 2 or 3, like pathology 1, 2, 3, or something like that. It's very, very nice. I really studied, so pathology, to me, it's kind of weird behavior compared to characteristic 0. Okay, and this is the example in characteristic 2. So I construct 2 guys. So one is, I take this point inside P2, okay, in a fine, okay. With T, of course, in F minus F squared, okay. And I blow it up. So maybe I should change letters, H. So notation over P2F, the blow up of P. Okay. So what it turns out that if you do your like nice calculation, this is a P1 over F 1/2. Okay, so this is a P1 over a degree 2 extension of F. Okay. And E squared, let's see if you guess how much this is. in characteristic 2. This is coming from a blow up of a point. It's going to be minus not 1, but 2. Okay. Okay. Y is regular. Okay. But non smooth. With a twisted, what's called a twisted ordinary double point. Sure. Right, it does. It does. It's exactly the dimension of H naught of OE. Okay, so imagine the case over R. You have two P1s, so that is still minus 2 when you contract both of them over R, right? This is true also, like if you blow up a point, you see, two conjugated points in R. Exactly. Yes, thanks. Thanks for the question. Okay. That was not very clever. Maybe I stay here, just because I stay close to the example. So this is what I was saying is that, you know, when you blow up something which is not reduced over a regular or a smooth surface, you get singularity. Right? This is a standard phenomenon when you blow up something which is not a smooth center. Right? And this is what is happening, but you don't get. You get a point which is not smooth, but regular. So this is called what we call in the paper a ghost singularity. So this surface becomes non-smooth when you base change to the algebraic closure. This point appears as an actual singular point. Yeah, actual singular point. Okay. Now, just the remark: if you take L, the line y equals 0. There, inside P2, is lifts to a minus 1 curve. This is really a minus 1 curve, okay? Okay, but you see, like you have something. This is the same strategy, you know, if you take like a line in P2, you blow up 1 point, self-intersection is 0, you blow up another point, self-intersection is minus 1. It's exactly the same strategy, just that here we are blowing up something which is of degree 2. It's exactly the same thing. So you contract this. So L twiddle upstairs, okay? And let's do, so we get X. Is it coherent with everything? Yes, X, which is, okay, let me say affine. In affine chart, you can describe it as, okay, X naught, okay, let me use other, oh, it's good, X naught square plus X1, X2 plus T, okay, this is inside T3 over F. Of course, T is, as usual, is not in. I mean, T is like this. Okay. Maybe it's another T. Okay, maybe we should say S. S in F minus F. Okay. And so what happens is that you can take now. So X has as well ghost singularity, which is the point Q. And this one is just the ideal XY. Sorry, I should, okay, so you see X. Let me write the X1, X2, okay, in a fine chart. Okay, that's the singular point, the point. Okay, and now you blow it up. Okay. And now W is So you have a point which is singular, you are blowing up it. You're blowing it up. And now this point, which is gives geometrically singularity, is replaced by a line, which now geometrically gives a singularity. So this is geometrically non-normal. Okay. So, so this is what's happening. And actually, I mean, it comes with a fibration over P1 F. This is exactly what happens when you blow up a point and you get kind of a cone and you get a fibration. This is not a cone, but it's kind of geometrically it's a cone. That's what happens. Good. And now make a picture, maybe. So let me, never need some colors. I'll do my best to make it like reasonable. Okay, so we have P2 here. P2. You take this kind of, I would say, I mean, maybe geometrically is this, right? It's a point with a tangent direction, geometrically, right? Now you blow it up, and you get, this was Y, thanks, Y. And here you have this kind of colors. Okay, even worse, maybe, okay. Here you have your Gauss singularity with an exceptional divisor. Okay, this is a Gauss singularity. Then you get a contraction here, and this is X. This is a del Pezzo of degree 8, right? Is a quadric in P3, right? So here, see, you have your guy here, and now you blow it up, and this is so this is a W, and this produces a line of geometrical singularities. Okay, so this is a isomorphic to P1 over F1 half. Again, this actually comes with a. Okay, so after 3 weeks of Cremona, this should like ring a bell, hopefully, right? Okay, so you see, this is really like circuits of links. Those are circuits of links which do not exist over perfect fields. Okay, this is a type 2, and this is of type 1, hopefully, or 3. Okay. I think 1 and 2. So, in wrapping up everything, yes. So what we did, maybe let me write it here. So let me state it as a theorem, which is by Bernasconi. Zimmermann. This is in 24. So say classification of rational Mori fiber space. My fiber space is over surfaces over imperfect fields. Rational, okay, this is the key thing, okay? Plus circuits of links. Okay? Kind of, we basically need to understand. Okay, classification is very vague. It's not that we actually classify them. What I mean is that we check the numerology you can get, and we produce examples when there are new examples, basically, okay? So this is like the work, you see, like if you look at the work of Vysotsky, Manin, you can really like look at the list, all the numerologies there. And the point is that over perfect field, some cases do not appear, but they could a priori appear in this case. Okay? And you understand, like, I guess, after Julia's mini course, which I missed, so hopefully I'm not saying something wrong. This is useful to understand Cremona, like understanding circuits of links and Mori fiber spaces, rational ones, is good for Cremona. So maybe the last thing I want to stress here. So let me give you a statement: need to bound pathology. Okay, so this is basically the key point. So what I mean by bound pathology, I mean, okay, assume that there is really like a new link and stuff. Maybe we can bound the characteristic, say this only happens in characteristic 2 and 3, this kind of statements, okay? But the statement I want to show you is the following, which is a little bit in the spirit of under the carpet. The theorem by us is the following. So if you take X geometrically integral del pezzo surface of degree d, which is minimal. All right? So if X is not geometrically normal, then it is birationally super rigid. Okay, unless P and D is 2 and 4. This is the case which actually okay. So this in particular implies that if it's birationally super rigid, it implies that it cannot be rational. Okay? So basically, being for the del pezzo geometrically not normal, basically is excluded. We can put this apart. We can always assume that our del pezzo surface is geometrically normal at least. So X is not rational. So just let me finish with just a joke, okay? Like, the thing is that I was presenting this in the UK, and then because basically the key ingredient for this is Miles-Reed classification of non-normal surfaces. Okay, this is the key ingredient for this. And then Miles-Reed, has this habit of like giving funny names to things, okay? And so I was thinking, okay, but you see, like those are surfaces. I'm saying, if they're pathological, they're rigid. So this is a rigor mortis statement. Okay. So it's so the pathology is so serious that actually it's rigid. It's very, very rigid. It's birationally rigid. Okay, that's why. And with this, I stop. Thanks a lot. Oh yes. Should I? Open.
This is a time for volleyball. So who have questions? Okay.
Thank you for the interesting talk. Can you develop further about superrigidity?
Yes, sure. So, okay, the idea is the following. So, Miles-Reed classified over algebraically closed field non-normal del pezzo surfaces, meaning that he just checked, like, basically, what is the normalization and what is the conductor. Okay, he classified everything. This is like a finite list, okay? And what happens here is that, so there's a work, okay, of Patak Fabio Waldron and myself and Stefan Schröer. So what we studied is basically which kind of, so assume that your surface is geometrically non-normal. So which conditions you get on the characteristic. So it turns out that the characteristic is only possible, this can only happen in characteristic 2 and 3, okay? And then you go through the list. And you proved it. So basically, it's just going through the list. And yeah, at the very beginning, we missed this case, okay? But this is like, something you can deal with. It's also like not rational. But so here, you take a del pezzo of degree 4. You can blow up a rational point. So now you get a cubic delpetso of degree 3, and these fibers over P1. Those are, and what you get is, if it's geometrically non-normal, this is going to be a wild conic bundle. So the generic fiber of this fibration is geometrically non-reduced even. It's what happens.
Something stupid about this characteristic 203. Is it just related to the fact that except for cubic surface, everything is intersection of plane
Except for
characteristic 203, is it related to the property that if you have cubic surface is a side, all the other guys are naturally intersection of points?
not really. So the way I see it is like basically for surfaces you have like the maximum length extrema rays. And so what happens is that to stay delpetso, basically you have a control on the Picard class of the conductor. This is basically the idea. So you have your delpetsos, and you need to be delpetso. So like you want that if you just take the canonical divisor minus the conductor, it still stays delpetso, something like that. This is what it is actually. You just get P2, Hilbert surface, and yes, so that's actually the way. Thanks a lot.